Hello everyone, welcome to this online course on material science. I believe this is lecture 11 in the module 1 on magnetism, right? And in the last lecture, if you recall, towards the end, we were discussing about the concept of canonical momentum, right? And the canonical momentum will be useful to understand the diamagnetism inside an atom, right? Because let's say in an atom we have number of electrons, right? And those electrons are moving in certain path, right? The question to ask is that what is the total kinetic energy, right, of that atom? So you have to know the individual component of the kinetic energy of the individual electrons, right? So the idea is that the total kinetic energy operator should be the sum of the individual kinetic energies of the electrons, right? But I have mentioned usually the kinetic energy is denoted by T, the standard notation. So T should be a sum over all the electrons, which, right? So Ti is the kinetic energy of the ith electron, right? And usually, if you are not considering magnetism, then this Ti, the kinetic energy, is defined. The sum stays there as the momentum of the ith electron, right? Which is an operator square divided by the mass of the electron, right? But when we discuss or when we try to understand magnetism, the idea is that we need to replace this old or the ordinary momentum operator with the canonical one. So idea is that we need to replace Pi with Pi plus the charge of the electron times the magnetic vector potential. So these are all vector operators squared, right? And then we have a twice m factor outside. That's the total kinetic energy operator of an atom having a number of electrons. Let's say that number is Z. So you need to sum all the kinetic energy component of individual electron. Now look at this quantity, right? We have some sum and this quantity. Let me evaluate the quantity here, right? So this is Pi plus Ea squared. It means we need to dot this with itself, right? The dot product of the vector. So we have P plus Ea dotted with Pi plus Ea, right? So when you multiply out this expression, you will have four quantities, right? Let me do it slowly. So the first one is Pi dot Pi. So that's a vector operator dotted with itself, the momentum operator, right? Now the next one, we are dotting the Pi with the Ea, right? And for convenience, let us put on also an ith index so that we can differentiate. This is the magnetic vector potential filled by the ith electron, right? Just to make it more explicit, right? So we have Ai. Now we are dotting Pi with E times Ai. So E is just a number, it goes outside, and we have two operators, right? Pi vector times Ai vector operator, right? Then we dotted this with this. So now we have first the Ai, then the Pi, right? So momentum comes next. The last one is E squared times the vector dotted with itself, the magnetic vector potential. So that's E squared times the vector itself, the magnetic vector itself dotted with itself, right? Now we have four terms here. So this first term, that's easy, right? That's just the square of the momentum operator vector. Now let's examine what we have in these two terms, right? This is an operator, that's another operator. So in this expression we have pi first, then ai, and in this expression we have first ai, then pi, right? And I told you before, as these are operator, there is no guarantee that p dot a is equal to a dot p, right? If they are equal, we can just add them, right? But recall, in ordinary vector calculus, right, we know for sure vector a dot b is equal to b dot a, right? No problem of ordering because these are ordinary vectors. But here they are vectors but vector operators, right? You have to be careful. Let us assume that we know that this is pi dot ai is equal to ai dot pi, right? So our assumption here, and we will see why that is true. Our assumption here is that pi dotted with ai is the same as ai dotted with pi. We can change the order. And from the previous lectures, you understand this expression is telling you that the momentum operator is commuting with the magnetic vector potential operator, right? That's why you can change the order. Let us assume here this, and then we can show why this is the case later. So if this is 2, then we can just add these two quantities, right? So we have 2a, and we want to write the terms in this order, pi dot the ai, assuming they commute with each other, the p and the a. Okay, and the last term is e square, and you can see this is a vector times itself, so that's nothing but the vector itself squared, right? And do we know the expression for the magnetic vector potential? Yes, we know. So let's put the expression for the magnetic vector potential here. So pi stays pi square plus 2 times the charge of the electron. We have pi here, and then in terms of this ai, we know from the last lecture that's the magnetic vector potential is nothing but the magnitude of the cross product between the magnetic field and the position vector squared, right? That's the expression for ai. Sorry, this is, there is no square here. That's the expression for a. And then the last term, you can see, if this is the a square, right? So we need to square this up. So that should be e squared by 4, and then b cross r square, right? Let's put the hat just to be more accurate, right? Okay, so that's about it. So we have 3 terms here. These 2 and these 2 get cancelled each other. And now let's process these 3 terms a bit further, right? This one stays the same all the time, and this one stays the same also. For example, we have to remember what we are trying to calculate, right? The kinetic energy of total energy of the electron. So we have some sum, and there is a twice-m factor outside, right? But we are only evaluating this term, which is these 3 terms, right? So if I want to collect those terms in the kinetic and total kinetic energy equation, then we will have something like, we have a sum, and we also have a twice-m factor outside, 1 by twice-m, and then the sum. The first term is pi vector potential squared, that's the one. Then we have E times pi, right, the momentum vector dotted with b cross r, right? Just check this expression. Now the last term, right? So this one is operating on the whole of this term. So then the last term is e square. You can see e square by 4 b cross r magnitude square, right? So that's the total kinetic energy. Now let me comment on this term. So which, just to be more accurate, right, I think we need to put some I index here also, because we are considering the ith electron. So we should put an I index subscript for the position vector, denoting this is the position vector of the ith electron, right? Just to make it more explicit, then we have some I index here too, and we are summing over the I, right? Now the sum is over all these three terms. Let me focus on this, the middle term, right? Let me write it down. What is the middle term? So the middle term is 1 by twice m. We have some sum running over, and then there is an e factor here. Let me bring the e factor out. So that's our e, and here we have pi vector times b cross r, right? So that's our expression for the magnetic vector potential. Now this is a cross two vectors, so a dot two vectors, right? There is a standard identity in vector calculus where you can see that any three vector, let's say a, b and c, then this relation holds. That's an identity. A dot b cross c, a, b, c are just ordinary vectors. Then we can write that this is nothing but b dot c cross a. So that's the standard vector identity. So if you apply this with a, b and c, assuming these three are a, b and c, then you can see this quantity can be written as b dot r, let me put the index here, ri cross pi, right? Now this sum will go here because we don't have any I index here. Magnetic field is uniform, so we have 2 by em. We have the magnetic field times the sum on ri times the pi, right? And do you remember what is this quantity? This is the angular momentum of the ith electron, right? And you are summing over all the electrons. So this quantity is nothing but the total angular momentum, right? Which is an operator. So this middle term in the end looks like E by twice m, then B dot the angular momentum operator. Now, remember the important point that I have mentioned in the previous lectures, that in the diamagnetic atom, we are considering the closed shell, right? For the closed shell structure, do you remember the total angular momentum vanishes, right? So idea is that then this term we can put 0 for closed shell structure. That's the important point we need to understand. That's why I was repeating the same thing again and again, just to understand that we can set 0. Now you can see this middle term is gone. The first term is the pi square and summed over, right? This is an ordinary term, which is the kinetic energy of an ith electron, right? We don't care much about this term. So what is the term left? The third term, right here. Let me write out the third term. So we have e square by 4 and 1 by twice m. So e square by 8m and the summed over I, right? So the last term is e square by 8m, then b cross r, which is an operator, the r, whole square, right? And this term usually known as the diamagnetic H for Hamiltonian, and we know what is Hamiltonian operator. We have discussed it in previous lectures. So that's an operator for diamagnetic atom. And we also need to put the sum, right? So that's the outer sum. So we are summing over this expression, and this is known the diamagnetic Hamiltonian. And the reason we need this diamagnetic Hamiltonian, we will see with the help of this quantity. Now we can measure the susceptibility of the diamagnetic susceptibility of the atom. That's one thing. Another important point to remember is that the Hamiltonian operator always represents the energy, right? So by this operator, we can measure or we can estimate the energy of the diamagnetic atom, right? That's very crucial because we will see susceptibility can be derived from the energy expression, right? So we will see in these things in the next lecture, so that then things will be much clearer now. But let me finish this lecture. Before I finish this lecture, I want to stress on the point that here we assume that the vector pi operator commutes with the magnetic field or magnetic vector potential, right? We have assumed this one, but let me try to sketch why this is the case. So we have assumed that let's not worry about the index I because it's common, it's just specific to I. Let me show that indeed P and the magnetic vector potential is indeed commute with each other. So these two terms should be equal. It means that you can change the order. So for that, let us take the components of the momentum operator, which is in 3 dimensions. We all know, we have mentioned this in previous lecture, px, py, and pz. And in this problem, we also know what is the magnetic vector potential, right? Because we have derived in the last lecture, which was the x component was yb by 2, if I am not wrong, and the y component was xb by 2, and the z component was 0. So that was our magnetic vector potential, and we need to put hat in this order. Now let us find out what is p dot a, right? So we are dotting p on the left and a on the right. So we have to multiply component wise, right? So b is just a number, we can change the order, it doesn't matter. So the important thing on the left hand side, when we are dotting with p dot a, right? Let me calculate this quantity. Then we will have minus px first, right? That's an operator. Then the y operator, right? Nice. But we have some magnitude, we don't care, we can put it here. That's the first product, right? Then we need to product the second quantity, right? Which is py times the x, right? And both of them are operator, and we can put the magnitude b anywhere, and the remaining product is 0, right? The z component vanishes. So that's p dot a. Now let me find a dot p, right? So now we are putting a on the left and p on the right. Then we will have the y first and then the p's, right? So if I will at this one now, I can put the b anywhere. So let's put the b first, and then we will have y first because we have a on the left, and then px, right? Component wise we need to put the product. So this is just a multiplication, ordinary multiplication, right? We need to form the product of y and px, and then we have some factors of half right here. Don't worry about this factor. The important point is that now we will have x times py, and we can put b anywhere. Let's put it here. So the question is these two quantity equal to each other, right? You remember in the discussion of the commutation, I said px commutes with y, right? Px doesn't commute with x, but px commute with y. So it doesn't matter whether you write pxy or ypx, right? So these two quantities are the same. Here you have pyx, and you know x, pyx commute with each other. So you can write xpy, right? So indeed, in this product, it really doesn't matter whether you put p dot a or a dot p. And this is because the fundamental commutation relation that I have mentioned in the earlier lectures, that if the pairs are not conjugate, they will commute. Px is not the canonical conjugate of y, So they will commute. Py commutes with x. So the order doesn't matter. This shows indeed in this problem the momentum operator commutes with the magnetic vector potential operator. And I hope this convinced you it was okay to change the order here and put that extra 2 here, right? Because we are just adding this to 1. This might not be the case in other cases, so we have to be careful, right? Whether the operator commutes or not. I think that's about it, and in the next lecture we will start from the diamagnetic Hamiltonian, which is this one, and try to understand how to calculate the susceptibility of the diamagnetic atom, right? I think that's about it, and thanks for listening, right?